The Genspace project that's here at DLD, testing your DNA, can you tell us a little bit about that? What's the purpose behind it?
Sure, so this is basically a do-it-yourself genetic test that enables participants to determine whether or not they have a very specific mutation in their genome that will confer resistance to HIV-1 infection. So it's gotten a lot of press recently because some individuals have been cured of their HIV-1 infection basically through stem cell replacement therapy. This was a famous case that happened a few years ago where an individual had leukemia and HIV and was essentially given a bone marrow transplant from donors who were donor matched but also had this mutation, which was a CCR5 DLD13 mutation, which is a small chunk of DNA is missing, 32 letters. And the type of assay that we're going to be performing here, or the participants will be performing, is basically making millions of copies of that region using a technique called polymerase chain reaction. And you can do this on the table here, and you can buy this equipment on eBay. And when they make many, many millions of copies of the DNA, if you have this mutation, those pieces will be slightly shorter. And if you have a normal piece, it'll be slightly longer. And we have another technology here called gel electrophoresis, which in 10 minutes will separate those two sizes. Okay. And if you have the small piece, you can see it by eye because we'll have a dye there that'll cause it to glow or fluoresce. And the participants will be able to immediately determine whether or not they have a mutation in that location or not.
Brilliant.
And then they get a button and they can tell everybody that they're a mutant or they're not a mutant.
Okay. Yeah. And what is the great, I mean, it must have been a great leap to be able to do this DIY DNA testing right here at this venue. What's the great technology about it that made that possible?
I would actually, it's several enabling technologies, and also the market and society is caught up in certain ways. I'd say the great leap is essentially, other than the technologies have matured, also the costs have dropped considerably. So a PCR machine that used to cost 10 years ago $5,000 to $10,000. You can find older models on eBay for approximately $200 or less. We have one on the table that's an open PCR. It's an open source PCR with Arduino components that is sold from California in the United States for $600. We have a cheap commercial model next to it that's available for $1,800, but you can buy used ones, like I said, on eBay for less than that.
Who would be interested in buying it other than scientists and hospitals,
right.
Maybe?
So there's a big movement of citizen science that's using tools of biotechnology. It also has very immense social implications because in the United States at least 30%, if not more, of the human genome is patented by corporations. And what's the significance of that is that a lot of genetic tests which will tell you whether or not you're susceptible to, let's say, a certain cancer, cost a lot of money. Not because the equipment is expensive or because the chemicals are expensive, because we're showing you right now it's not expensive, but because somebody has a monopoly on it. You have to get a license because they want to make a profit, but the profit is exorbitant. So for an assay that in reality should cost $10, there's companies charging $5,000, $4,000 for. And the individual that's affected, this is having an effect on their ability to survive, because sometimes insurance won't cover it. So you're seeing this kind of push for people to test themselves. No doubt the medical establishment doesn't like that, but unfortunately in a lot of cases there's little alternative if the cost is so high. So you're seeing this democratization of medicine, democratization of citizen science, and we're just basically letting people know what's happening at the forefront, both scientifically, medically, and also sociologically.
What is the benefit for the medical industry or the hospitals or whoever owns the patent on the genome to have all this data? Why do they want to keep it?
To make money.
Just to make money.
Highly profitable. If you're selling a test that costs thousands of dollars and you're running thousands of samples, that's a lot of money, especially if it costs you only $1 to run the test, and you charge $5,000. That's a massive profit, right? So
you're breaking a monopoly, really.
Exactly,
with the
yeah.
New, and collecting the data, like the DNA tests that you do here, collecting all this data, what does that potentially show, as in maybe there are patterns that weren't known before, and because you're collecting many more now, you can maybe see something new in the future?
Oh yeah. So we're not doing the data collection for any analysis purposes. So that's fairly anonymous. People will find out what number they have, but because of the technology advances in genome sequencing, there's so much genetic data being accumulated right now. I personally donated my DNA to, well, not donated, I paid for a kit, and a company 23andMe has analyzed regions of my genome. And it's telling me some really interesting and potentially life-saving things about my own genetic profile. It's telling me which drugs I shouldn't take when I go to a hospital because it might have a toxic effect on me, but not for you. So that's potentially very useful information. But when you actually start to look at millions of people's genomes and you start to correlate certain patterns, then you start to get really powerful information as to what drugs you can give an individual to cure their particular cancer. I was just talking to somebody recently and I said, you know what, the fascinating thing to me right now is we may already have the cure for every cancer right now. We may already be able to cure every cancer on the earth, on planet Earth. We just don't know who to give the treatment to, because right now it's very kind of crude. They'll give a certain treatment, a chemical, to somebody who has breast cancer, and they'll have a study with 1,000 people that have breast cancer. Although breast cancer, we now know it's not just one category of breast cancer. You can have many different mutations that make cells basically divide uncontrollably. And having all of this genetic data available will allow you to essentially parse that information and say, okay, wait, breast cancer is actually an umbrella of a dozen or 24 or 100 different categorizable mutation states, and each of those several dozen groups, only one drug is effective against. So if you give one drug to that group of 1,000, you'll only be able to cure only 10 out of that whole 1,000. And then, unfortunately, because you designed your study in this way, you throw that whole thing out and you say, well, that drug didn't work. It only helped 10 people, so it's not effective compared to the standard aggressive chemo, which also has major side effects.
Yeah.
But if you run all these studies, you're throwing out continuously drugs that really work, but you just don't know, tragically, who to give them to.
Again, that's an industry question, isn't it?
That's an industry, but it's also a data analysis problem, because once we have kind of enriched our understanding of the genome, we could say, wait a minute, we've thrown away all of these drugs that would have helped you and the guy behind the camera and myself, but we didn't, but if we had those 3 drugs and gave them randomly, we might all get the wrong one and say, well, they don't work. But that's not true. Drug A will work for you, drug B will work for me, drug C will work for him. But unless I know your genetic profile and my genetic profile and his genetic profile, I wouldn't know who to give that drug to. So that's why I'm saying potentially we may already have the cures. We just don't know who to give them to.
Great. Thank you so much.
No, you're welcome.